All right, everyone, welcome back. Assuming you watched the last video, we have 12 lectures down, 26 to go. It is another hurricane cancellation class period. So yeah, we're going to do another video. But note, exam 2, October 18th, covers chapters 12 and 13. Equation sheet is up. The suggested practice problems for chapter 12 is up. We won't finish those till the end of next week. But if you want to get a jump start during the cancellations due to the hurricane, feel free to take a look at those. All right, continuing our journey into 12.4, we're going to start talking about integrated rate laws. Don't worry, we're not going to be doing any calculus in this class, but they are the byproduct of calculus. And so in 12.1, we talked about this rate expression where we said the rate of reaction is equal to the change in concentration over the change in time. And we can take this equation here, use the stoichiometry, figure out how the concentrations of each of these guys change with respect to time. But we said that rate is dependent on concentration, so the rate changes depending on the concentration. So we use this instead, this rate law, which is a relationship between rate and concentration as dictated by this K, or this rate constant. And so we have rate laws where we have to experimentally determine x and y. They are not dependent on the stoichiometry. But if we want to calculate changes in concentration with respect to time, or how much time it'll take to change the concentration, what we do is we actually combine both these, do a little bit of calculus, and we come up with something called the integrated rate laws. It basically says, you can set those guys equal, you can do a little bit of algebra, and you can figure out a zero-order reaction. The relationship between initial concentration at times t, is going to be dependent on this t and this k rate constant, so the amount of time times the rate constant. For a first order reaction where the rate law is rate is equal to k to the concentration A, natural log of AT is equal to negative k times t plus the natural log of A naught. This is the initial concentration. This is the concentration at time t. And the second order reaction, rate is equal to k times concentration of A squared. There's your relationship there. And so you can see in this case, all the variables are the same. It's just a question of what the relationship between concentration change and time is. Is it 1 over A? Is it natural log of A? Or is it just A? And so you'll note these are all in y equals mx plus b form, and that's really convenient because we can use these straight line graphs to figure out which one it is, or we can make predictions. And so basically what we're doing is if we know a concentration, we can figure out concentration at times t. Similarly, if we know an initial and a final, we can figure out t as long as we know the slope. And so as long as we know 3 out of the 4 variables, we can figure out what the 4th variable is. And so what you do experimentally is you'll actually figure out concentration change with time, graph it 3 different ways. Which one of these gives you a straight line? That tells you something about the order of the reaction. And note that it'll only be a straight line on one of these types of graphs. And 2 of the 3 will not be a straight line. And so yeah, we can figure out concentration change with time, and as well as what the order of the reaction is from that relationship. And so we have 0, first, and second orders, and I think it's worth actually thinking about what these reaction orders actually mean, because they tell us something about the reactions. So one cool example of a 0-order reaction is a process of drug elimination. And so if you administer a drug to the body, typically it's going to get processed in the body according to a 0-order reaction. Which is weird, right? Because according to the 0-order equation, it is not dependent on the concentration of material. And so in this case, if you deliver 1,000 milligrams of something to the body, and your body can only process it at 100 milligrams per time, or 100 milligrams per minute, that is going to be the rate. And that rate is not going to change. It's going to be rate limited by something. And so you're going to get a straight line, concentration versus time, and you get a rate law that is rate is equal to K, or the rate constant of what the reaction is. And so one example of this might be enzyme kinetics that are limited by binding of the thing to the enzyme. And so let's say you have all these red spheres here, and the slow step is getting that red sphere in there and putting that red sphere out, which means it's not limited by how many red spheres you have, it's limited by the reaction process itself. And so that could be an example of a 0-order reaction. It's not dependent on the concentration because it's rate limited by something that's not dictated by the concentration. And so, yeah, whatever the drug is, it's to the 0 because the concentration of this doesn't change how fast this process happens. Other examples of this, there's a bunch of surface catalysis where it's limited by the surface and how fast things can bind and release from the surface. And so put as much concentration as you want in solution, similar to the enzyme kinetics. It is not dependent on the concentration of whatever that species is. And so if you want to turn NH3 into N2 in hydrogen, which is a hydrogen generation mechanism, it's actually zero order with respect to NH3, and so the rate is proportional to K. K is largely dictated by the surface, or entirely dictated by the surface, and not the concentration of NH3 floating around in solution. First order reactions, these are much more common. And so one example of this is hydrogen peroxide turning to H2O plus O2. You might not be directly aware of this, but probably in high school chemistry you guys did something called elephant toothpaste, which is actually this process here. You take a little food coloring plus soap, plus you add a catalyst. You can turn, standard grocery store hydrogen peroxide into oxygen, and that's actually what makes this happen. You're essentially bubbling oxygen through soapy water, and that's making the bubbles, and the color is whatever food coloring you add to the reaction. And so if you actually monitor the kinetics, and you can kind of see it here, right? The reaction slows as the reaction progresses. Goes really fast quickly and then slows down over time. It's because the concentration of H2O2 is decreasing and the rate is slowing down. And graphically, it would look something like this. Or we could graph it in a slightly different way. The natural log of that concentration versus time gives us the straight line graph. We love straight line graphs because it tells us what the order of the reaction is. And so in this case, the straight line is x is t. That's here. Slope is negative k in this case because the slope is going down. Natural log of H2O2, natural log of A to the T, plus the intercept is natural log of A naught, which tells us that this is a first order reaction with respect to H2O2. And that's what we see in the rate law here. Rate is equal to K times the concentration of H2O2 to the 1. And so we just take this graph here, graph it three different ways: concentration versus time, natural log of concentration versus time, and 1 over concentration versus time. The one that gives us straight graph, that tells us the rate law of the reaction. Rate is equal to K times the concentration of H2O2 to the 1. So yeah, elephant toothpaste, an example of a first order reaction. Note that they should be wearing goggles, but so it goes. All right, second order reaction. These are bimolecular reactions. You'll learn about bimolecular reactions a lot in organic chemistry, but this is just one example. Two HIs going to H2 plus I2. Sulfur iodide thermal chemistry for H2 production, but you get a graph that looks something like this. The concentration change in HI versus time looks like that. If we graph it as 1 over HI, we get a straight line. That is a second order reaction. And so this basically tells us rate is equal to K times the concentration of HI squared. It tells us that two HIs have to interact for this reaction to occur, and that's occurring in the rate limiting step. And so there's our straight line graph for our second order reaction. Just a quick side note, third order reactions do exist, but they are very rare and they are very slow. There's probably many of these that exist, but we don't see them often enough to actually measure them. But here's one particular example. If you take two NOs plus an O2, and that's the stoichiometry in the reaction. Coincidentally, this is a third order reaction with a rate law that looks like this. Rate is equal to K times the concentration of NO2 squared times O2 squared. And the reason these are so rare is because it basically requires all three of these guys to combine and hit at the exact same time with the correct orientation and correct energy for a reaction to occur. And so you guys can do this like playing a game of billiards, right? You throw billiard balls on a table or whatever it is. Getting two of them to hit is really easy. But getting three of them to hit simultaneously is a very, very unlikely event. And so you're essentially relying on just statistics of collisions and getting all three of those collide simultaneously. That's why it's so rare and slow. And so third order does exist where you have three things that need to collide in the rate limiting step, but it is very rare. Typically, if you're going to combine three things, you need some kind of catalyst to put those three things together. All right, so the other part of these integrated rate laws is we can get half-lives, or we can discuss these in terms of half-life. And half-life, not just the video game, but half-life in terms of the scientific principle, is T1/2. It's the amount of time required for a substance to be reduced by 50%. And so there's nothing magical about half-life. We could have quarter life, we could have three-quarter lives, but half-life is just a really convenient descriptor in some circumstances. And it basically says, how long does it take for half of the stuff to go go away. And so if you have one half-life, you lose half the material, then another half, then another half, so on and so forth. The amount of material as it goes down, you can see the percent decreases as well. But how long this takes is really going to be dependent on the order of the reaction. And so we can do the algebra to figure out what the half-life and how that relates to the rate constant and concentration if that's the case. So for zero order, T1 half is equal to concentration divided by 2K. First order, T1 half is equal to this number divided by K. Note this doesn't have any concentration dependence. The half-life stays the same no matter what. And a second order, T1 half is 1 over K times the concentration of A naught. And so both zero order and first or second order are dependent on the concentration of the material. First order reaction is not dependent on it. But again, this is doing the same concentration time equations, but all we're doing is cutting the concentration in half. And this is what the T1 half effectively is. And so there's a lot of different reasons you'd care about T1 half. This is a general descriptor. Like biology and medicine, you have half-life of something that you've put in the body. How long does it take half of it to eliminate from the body? And so this could be pharmacological, physiological, radiological. Something is going away, and it takes a certain amount of time for half of that material to go away. Electrical engineering, you have RC circuits, and so sometimes you care about the half-life of current flow and how long it takes half the current to disappear. That has to do with the resistance and the capacitance of the circuit. Nuclear science, it's a radioactive decay. How much has half the nuclear decay gone away? And so half-lives are really common, used in a lot of different fields, but it really comes down to how much does it take for half the stuff to go away. And so the most common place we casually hear about this is probably in this idea of radiometric dating. Basically says, radioactive decay is a first order process. And so if you know the half-life and you know the time it takes to get half the concentration gone, you can measure concentration and figure out how long something has been around. And so this is used in biotracers, something you can put inside the body, like this iodide 131. It undergoes beta decay to make xenon, and so the iodide disappears over time. And so you can effectively use this to track iodide decay within the body and where it goes and how long it takes to get there. Another common one is carbon dating, like if you want to date an old book or an old piece of cloth or something like that. There's a certain portion, it's like 1.1% or something like that of carbon-14. That carbon-14, normally it's carbon-12, but in this case there's a certain fraction of carbon-14 that undergoes beta decay to nitrogen. And so if you know how much carbon you started with and you figure out how much carbon-14 is left after a certain period of time, you can calculate the number of years it took to do that. And that's how that dating works. You assume natural abundance is at the start, the carbon-12, carbon-14 ratio, and then as that carbon-14 goes away, that ratio changes. And so you can use that ratio to figure out how long something has existed. And so a really cool example of this with like old Earth and in geology is uranium dating. And so you have these zirconium silicon oxide like crystalline materials that grow in the earth, and this is just a normal zirconium material, but occasionally you'll get some uranium to incorporate, and so that uranium will actually substitute for some of those zirconium ions, and they will be inside that crystalline lattice. But what's crazy is over time, some of that uranium will actually decay into lead. And so here's the decay process. We won't get into details, but you start with uranium-238 inside the crystal, and eventually within the crystal it turns into lead. And so it's still in there. The lead is within it. But that lead didn't come from something external. That lead is only generated through this decay process. And so it won't incorporate in the crystal initially. It'll only stay in there if it's generated inside that crystal. And so we know how long this half-life is. We know how long this process right here takes. And so what's cool about this, if we want to date really old rocks that contain some uranium, we can look at, okay, some of the uranium turned into lead, which means if we calculate at the end, we have the ratio of initial concentration, which in this case, every one of these leads was initially uranium. And so we had 8 uranium at the start. Now we have 4. That is half the amount. That means that this rock is 4.5 times 10 to the 9th years old, which is kind of crazy. And so it's a first order reaction. We know what the half-life is. We know what the rate constant is. And so if we know the ratio between the two, or how long it would take to get half the material away, we can date the rock according to the ratio between these two. And so if it was a quarter, then it was, a quarter life, basically. And so, yeah, we can use the ratio of those two things to date rocks that are really, really old. Not just date them, but date them very, very accurately. And so for Mesozoic rocks, this is 250 to 266 million years old. We can date those accurately within 2% error. And so you can take separate samples that we know similar events occurred in the past, and we're going to get within 2% the age of them based on this radioactive dating. All right, so there's our summary. We have zero order reactions, we have first order reactions, we have second order reactions, we have the concentration time equations, which is these three guys. We have straight line graphs. Remember, it'll only be a straight line on one of these, or maybe none of them. And we have half-life equations. We basically take these and say, if this is 2 and this is 1, what does this rearrange to? The answer is that. If this is 2 and this is 1, what does it rearrange to? That. And if this is 2 and this is 1, we can rearrange the equation and get that. And so these half-life equations are just a special case of concentration time equations, with the concentration decreasing by half. All right, time to dive into the clicker questions. Obviously, we can't do them live. It's unfortunate, but we're going to do them now. So feel free to pause and answer this question. All right, so one thing that's cruel about this is I could ask you to answer this question, memorize equations, but I'm not going to do that. Instead, we're going to have this table here. This is actually on your equation sheet for exam number 2. I don't expect you to memorize this. I don't care if you memorize this. The answer is this is on Google if you want to look up rate laws and concentration time equations and half-life equations. That information is readily available to you. At no point are you going to be on a desert island where you have to memorize a half-life equation. So we're going to make your life easier for the remainder of these questions, and we're going to include this concentration time equation. And so here we have a reaction with a rate constant in units per second. Which equation would you use to determine the concentration of A at some time t? And so you want to know which concentration time equation you can use here. It doesn't tell us it's first order, second order, or zero order, at least not directly. And so this harkens back to what we learned in section 12.3. If K has units of per second, there is only one rate law that it can be, and the answer is this one. And so if this is per second and this is molarity per second, which means the concentration time equation that we would use is this one right here. The answer is B. Likewise, the half-life equation we would use. And so this, just telling us the units on rate constant, tells us it's a first order concentration with respect to reactant, and it tells us which concentration time equation we can use, which is B in this case. All right, question 2. What is the rate law for reaction 2A going to be? All right, so some of you have figured out the answer is D, not enough information. All right, we haven't been given a rate constant. We haven't given an order of reaction. All we've been given is a equation for this reaction. And so we can know for sure that the rate of disappearance of A is going to be twice as fast as the rate of disappearance of A will be twice as fast as the appearance of B. But we don't know what the rate law of this reaction is because we haven't experimentally determined X and Y. We don't know what the order is. We don't know what the rate constant is. This does not give us enough information to answer this question. But let's try it again with some additional information. What is the rate law of this reaction? Go ahead and pause. All right, so this one tells us the change in A can be described mathematically by this equation here. We look at that equation and say, okay, it's a very specific relationship between K and concentration of A. And so we look down here at our table and we see this concentration time equation relates to a second order rate law. Rate is equal to K times the concentration of A squared. The answer in this case is C. And so in this case, it gave us the relationship. It gave us how concentration relates to the rate constant in time. And the only way to describe that is with a second order rate law. The answer is C. All right, so now we're given a graph and we have to translate that to a rate law. Let's go ahead and pause. All right, so a few different ways we can think about this. We know from the graph that the concentration of A is changing linear. And so we could look back at our y equals mx plus b, and we could say, A is decreasing linear. Time is proportional to concentration. If concentration of A changes, then time t changes, and those guys are proportional. We could say this is a zero order rate law. The other thing we could look at is saying, if we did the change in x over the change in y, or we did, the derivative of this, the tangent to the slope, we would say the rate doesn't change at all over the course of the reaction, which means rate is not dependent on the concentration of A. The rate law that shows that is this one right here. So your answer is A. So you can either memorize what the graphs look like. A straight line with A versus T gives you a zero order reaction. You could look at this equation here and say A is proportional to T. Note down here, if A changes here, it'll change T, but it'll change it in a logarithmic relationship. Similarly here, if we change A, 1 over A is not going to change linearly with T. And so we have to rule out these two equations with this particular graph. The answer is A. All right, next question. Go ahead and pause. Which of the following cannot describe the rate law for reaction of A to C? All right, so there's only a few things we can be sure of just looking at this data, right? And so one of them is that it is not A. As we showed in the previous question, question 4, if rate is equal to K, you're going to have a zero order reaction. That means concentration of A should decrease linearly with concentration of T. And so if it was a zero order reaction, we'd expect a straight line. It is definitely not a zero order reaction. The next thing we could ask ourselves is it B or is it C? And it's kind of hard to tell from this graph. And so what we typically have to do is change this data, take the Excel spreadsheet, take whatever this Y data set is, take 1 divided by that Y data set, or take the natural log of that Y data set and graph it in 2 additional ways. And if I had to guess, I would say this is probably a second order rate law. It's not necessarily this logarithmic. It's more pronounced than that, but I don't know for sure. So yeah, you can't know for sure if it's going to be first order or second order, but it's definitely not a zero order reaction. So it is not A. All right, another graph. So go ahead and pause. Let's figure out what the axes on this graph is. All right, so we have a concentration versus time graph, but we forgot to draw the units here. But there is information here that helps us figure that out. We basically want to figure out, which one of these concentration time equations, y equals mx plus b. If we know that, we can figure out what the x-axis and y-axis. Spoiler, the x-axis is always going to be t, so we need to figure out what the y-axis is. And so options A, B, and C are still reasonable. We have to figure out what the y-axis is going to say. And so the only thing that gives us a hint here is not the reaction. That doesn't tell us anything. Instead, we need to look at the units of K, right? Units of K in molarity -1, seconds -1. Well, there's only one rate law that has these units, and that's a second order rate law, right? If rate is molarity per second, this is molarity squared. We need to cancel out at least one of those molarities. You do that by having a molarity -1 here. Those cancel. This is a second order rate law. If it's a second order rate law, then the graph needs to be T is equal to X, 1 over A is equal to Y. So T is here, 1 over A is here. The answer is C. And so we have to know something about the rate law. This tells us what type of rate law it is. So let's do a slightly different version of that, having a slightly different unit here. Go ahead and pause and answer this question. All right, so looking at this one, very similar question. The only hint we have of what the rate law is molarity per second. The only rate law that coincides with molarity per second is rate is equal to K. This is a zero order reaction. And so for zero order reaction, we would expect the relationship between T and concentration of A to be linear. So we could suggest T here and A here. But it turns out the answer to the question is D. None of these are correct. And so A is the correct graph, concentration of A versus T. But there's a problem with this line here. And that's if this is a zero order reaction, what should be happening to the concentration of A versus T? The answer is it should be going down. And so this should actually have a negative slope. And so this can't be any of them. It's physically impossible. The graph is concentration of A versus T, but this cannot represent what happens to the concentration of A. And so there's a couple ways we could look at that. We could go back to our tables and we can memorize, okay, this slope on second order goes up, first order it goes down, zero order it goes down. Note that the concentration is always decreasing, but how we graph it changes it. And so this is just graphing concentration. This is just natural log of concentration, so it changes how fast it goes down. 1 over concentration, because this number goes down, the graph always goes up. And so one way to think about that without having to memorize it is looking at down here at these equations here. And so this one has a positive slope. Positive slope means it goes up. This has a negative slope, negative k. This has a negative k. That means these two should have a slope going down. And so while this suggests it's first order, time versus concentration, it should have a negative slope and it doesn't. So none of these are correct. Bit of a trick question, but it's trying to get to emphasize to you guys, it's not just graphing the relationships. The slope on that and how A changes does matter. All right, pause and answer this question. All right, so it's not explicitly mentioned in this question, but this is a half-life question. It's basically saying us, we have a starting point and we want to figure out a concentration over time. And so there's two ways we could do this. We don't have to do half-life. We could say, it's first order. So first order tells us these are the equations that we're dealing with. And so we could take this natural log of A times natural log of A naught minus KT. If we determine a rate constant for this from this data set here, we could figure out, what this plug and chug our numbers in there. Or we could recognize that, well, the half-life of this first order reaction is independent of concentration. And so if it changes by 10 in 1 second, that's the half-life, right? The half-life is 1 second. And so if we go 1 to 2 seconds, it's going to decrease by half again. And so the answer in this case is C. And so note that's why half-life equations are convenient, because it's decreasing by half, it's going to decrease by half again. Or we could figure out what's the rate constant from this, figure out K, we figure out T is 2, concentration initial is 20, have this be an unknown, solve this algebraically and get an answer, that answer will be 5. But if we know that it's first order, half-life is concentration independent, it decreases by half, the answer is 5. All right, next question, go ahead and pause. All right, so the key here is what expression could describe the reaction. And so the half-life of some compound A decreases with time. So the half-life is changing. So we know it's not a first order reaction, so it could be a zero order or a second order. But the trick on this question is none of this tells you what the order of the reaction is. And so we know that A is going to change with time and the half-life is going to decrease with time. But what we don't know is what the rate law for any of these reactions are. So any of these could be a possibility. Any of these could be a zero order or second order reaction. We don't know unless we figure out what those exponents x and y are, or we're given a rate constant, or we're given a graph that lets us figure it out. The point is any of these could be described by a half-life that decreases with time. And so we can actually figure out whether it's zero or second order at the very least, and it's because the half-life decreases with time. And so if any reaction, the reactant is going to decrease with time. We know A is going to go down, and we know in this case the half-life also goes down. And so we can compare these two equations here. If A decreases, T1/2 decreases. If A here decreases, T1/2 increases. And so we can rule out, just based on this information, that this is a zero-order reaction. But we don't know what the chemical equation for that zero-order reaction is, so the answer is all of the above. It could be any of these. It could be none of them. We don't know. We don't have enough information. All right. Now we're going to try to figure out a rate law from it. So spoilers, I realized I gave away the answer to this question in the previous question, but we can figure out a rate law. We cannot figure out an equation from this. And so like I described previously, the half-life of compound A decreases with time. That means T1/2 goes down as A goes down. The only relationship that gives you that is this one right here. T1/2 equals concentration of A over 2K. That means this is a zero order rate law. The answer is A. So we can figure out the rate law of the reaction, but we don't know the stoichiometry or the actual equation of the reaction. All right, question 11. Let's pause and figure out the answer to this. All right, so this one's a little bit challenging. I mean, we could plug and chug numbers in these equations if we know what the equations are, right? Because we know how time is changing. We could figure out, potentially figure out a rate constant for the reaction. But we need to figure out which equation we could use. And so one way to think about this is, look, we have concentration is changing by half, right? 10 to 5 to 2.5 to 1.25. And if this was a first order reaction, we'd expect the half-life to be the same, right? And so it would be 0, 1, 2, 3. Every 1 second it loses half. But that's not what's happening here. You can see that the half-life is getting longer as the concentration goes down. And so if concentration decreases and the half-life increases, the only equation we can use to describe that is the equation right here, right? Because the half-life is, this is going up as this is going down. If this was going down, this would go down. It can't be this one because it's concentration dependent. We can rule out these two guys. This is the only equation that can describe the relationship here. And so just from this data in the table alone, we could graph it, we could figure out straight lines, or we could recognize that the half-life increases as concentration decreases. This means it's a second order reaction. It would have a rate law that looks something like this. But the question wants us to actually calculate a rate constant. And so we could do this a few different ways. We could pick any one of these data points and plug and chug the math here, but we're going to just pick the first one, right? And so if we take initial concentration of 10, plug it in there for A naught, the time it takes for that to decrease by half is 1 second. And so 1 is equal to 1 over 10 times K. Move the K over here, move the T over here. K is equal to 1 divided by 10. That gives us this one right here. It's 0.1 because it's second order. The answer is C. And so make sure the units are right. K, the units on K for a second order reaction, it's molarity minus 1, second minus 1. C is your answer here. A gives you the same number, but it can't be molarity per second because that would mean it's a zero order rate law. And so, yeah, the answer is C. Note again, we could do the math on any of these, right? We could take the, initial concentration of 5, put that in there. The half-life for that 5 to decay is 2 seconds, so we'd put a 2 over here. We switch the K and the 2, just algebraically. 2 times 5 is 10. 1 over 10 gives us 0.1 again. And so the K is equal to 0.1 molarity per second. It will always give us this answer of C. And so the half-life is increasing as concentration of A decreases. It's a second-order reaction. We can plug and chug in this equation with time 0 and half-life we determine from this, and we can figure out the rate constant, and we figure out units from what the rate law is. So yeah, there's all these things tie together. Spend some time wrestling and relating those variables. And so that closes out our second recorded video. Here's to hoping that we're back in class on Monday. If not, I'll do a recording for Monday as well. But this is all we have for now. Hope everyone stays safe during the storm, and hopefully you have a little bit of time to watch these videos. If not now, then maybe over the weekend. But yeah, take a break between the pre-class video and the in-class video. And on the in-class video, yeah, hopefully you've learned something from the clicker question. All right, we'll see you guys on Monday.